We previously looked at the reactions of two carbonyl-containing groups, which was the aldehyde and the ketone, and these both had either a hydrogen attached to the carbonyl carbon or carbons attached to the carbonyl carbon. We looked at the oxidation of aldehydes, which just included the addition of an oxygen between this carbon and the hydrogen, which gave us an oxidation. And then we looked at the reduction of both the aldehyde and the ketone, where we just broke this double bond, the carbon-oxygen double bond here, and then added hydrogens across that double bond. So added a hydrogen to this oxygen, a hydrogen to that carbon, and this essentially formed alcohols. Okay. So we learned how to reduce aldehydes and ketones to alcohols, and then we also learned how to oxidize aldehydes. Now we are going to look at the carbonyl-containing functional groups that have a heteroatom, also known as an electronegative atom, bonded to that carbonyl carbon. So we are no longer looking at hydrogens or carbons bound to that carbonyl carbon. Now we have this electronegative atom here, whether it's a carboxylic acid, which would be an oxygen, an ester, which is also an oxygen. The difference between the two is what's bound to that oxygen. In the case of the ester, it is a carbon-containing group rather than a hydrogen. And then the amide, which is going to have a nitrogen bound to that carbonyl carbon, and then that nitrogen can be bound to hydrogens or other carbon-containing groups. What we're going to look at is how this carboxylic acid can be converted to an ester, or it can be converted to an amide. These are the two things we are going to look at. So let's look at how that is going to happen in a little bit more detail. Okay, so here we have carboxylic acids. This is part of our starting material. So we have carboxylic acids in our ester formation reaction, and we're going to have a carboxylic acid in the amide formation. So the difference between these two reactions is what this carboxylic acid will react with. This carboxylic acid will react with an alcohol, and that's how we're going to form the ester. This, in amide formation, it has to react with ammonia or some other amine in order to make an amide. So let's look at the ester formation reaction scheme here. So what will happen in both ester and amide, but looking at ester right now, this OH and this H are going to come together to form water. And then whatever is left over from your alcohol will bind to this carbon here, your carbonyl carbon, in order to form this ester. So this OR group bound to that carbonyl carbon now is the remaining part of your alcohol. These types of reactions are known as substitution reactions. Substitution. They're called substitution reactions because we're substituting this OH group here. That's going to be the case in both reactions. We are substituting this OH group with something else. In this case, that something else is coming from our alcohol to make an ester. Note that your ester functional group is this one here. An ester is defined as a carbonyl carbon bonded to another oxygen, and then that oxygen must be bonded to other carbons. So that is how you can form an ester, by substituting this OH group, by removing it and bonding it to this other H to form water. And now this oxygen is available to bind, to form a bond with this carbonyl carbon here. For amides, we are going to see something similar, where the OH group is replaced by the nitrogen-containing part of your other reactant. In this case, it was ammonia, and so you replace it with NH2 to form your amide functional group. Okay. Both are going to follow similar steps in the reactions that we're going to look at. We're specifically going to look at the formation of an ester, which is what this reaction is showing here at the top. We go from a carboxylic acid and we form an ester. This is called esterification. And then we are going to look at the reverse, because if you can make bonds, you can break bonds. And most of the reactions, all of the reactions we're going to look at are going to be reversible, meaning if you can go forward, you can go backwards. So we are not only going to look at the formation of an ester, but we can also look at breaking an ester or hydrolyzing an ester to return back to the carboxylic acid. So the other type of reaction we are going to look at is called hydrolysis. Hydro is referring to water. Lysis means to break. So when we go in the reverse direction, this water here that's part of our products now will now react with your ester in order to break this bond and return back to the carboxylic acid. We're going to do some examples of that in just a minute. We are going to, in a separate video, also look at the formation of amides and their hydrolysis as well. But the main point here is that what we are going to learn about ester formation and hydrolysis, the general schemes will apply to amide formation and hydrolysis. The only difference is that we're going to be dealing with compounds that contain nitrogen groups. Okay, let's look at ester formation, a reaction that is an esterification reaction. Okay. These esterification reactions are going to happen in the presence of an acid. So let's first identify our functional groups like we always do. So here I have acetic acid. I recognize that this is going to be a carboxylic acid group. So this is my carboxylic acid. And that's going to be characterized by this carbonyl carbon and the oxygen, that carbonyl carbon bonded to that OH group. Now over here on this side, I have ethanol. This OH group here is characteristic of an alcohol. And so I recognize that I have a carboxylic acid and an alcohol. When you have these two reactants together, this can react to form an ester and water. So how does that happen? Let's go ahead and track our atoms here. So what will happen in this reaction is this OH group will leave and it will combine with this hydrogen here from ethanol. So you need to locate the OH group in your other reactant, your alcohol reactant. So this is our alcohol. You locate the OH group and the hydrogen bonded to that oxygen will be removed and that will combine to make water. And then what is left is this oxygen here that needs a partner, it needs a bond, and so it will form a bond with the carbonyl carbon here that also needs a bond because we have removed this OH group here. So that is how we end up with this entire part of this alcohol molecule, the OCH2CH3. That entire thing is now bonded to that carbonyl carbon for which we removed the OH from. Let's look at another example. Here I have benzoic acid. First, let's look at which one is our carboxylic acid. The one on the left-hand side, the benzoic, is our carboxylic acid. And then we see that the other reactant that we have here is methanol. This OH group here makes it an alcohol. And it's in the presence of an acid. So we have all of the conditions here to do an esterification reaction. So we remove the OH, remove the H, these combine to form water. And then whatever remains of your alcohol, that is going to go ahead and bond to your carbonyl carbon that now also needs a bond. And that is how you get this OCH3 bonded to that carbonyl carbon. Okay, let's apply this to some reactions. So what product is formed in each of the following reactions below? Again, the first step in all of these reactions is identify your functional groups. So let's go ahead and look at this one here. This one should probably jump out at you at this point. It's a hydroxyl group, so that means this is an alcohol. Now let's look at this other molecule. This one's going to be a little trickier. COOH, this is something we've seen briefly before. This is going to be a classic way to write a condensed formula for a carboxylic acid. So what's happening here is you have a carbon double bonded to an oxygen, then that is also bonded to another oxygen, so that would be that oxygen here, which is in turn bonded to a hydrogen. So what I have here is this compound. The other tricky part about this question is that you do have another functional group, and that's going to be this one over here that contains the electronegative atom oxygen. So this oxygen here is bonded to a carbon on that side, a carbon on this other. So this functional group here is going to be an ether. Ethers here, so that's ETHER. Let's just go ahead and write that. This is an ether functional group. That is not going to do anything in this reaction because we have learned that a carboxylic acid in the presence of an alcohol and acid is going to react to make an ester. So let's go ahead and carry out that reaction. Now that we have identified our carboxylic acid here, and we have identified we have an alcohol in the presence of acid, we can go ahead and remove the OH group in my carboxylic acid. That's going to pair with the hydrogen that's bonded to that oxygen in my alcohol, and that is going to form water. So I'm just going to write that off to the side. Now let's look at what remains. This oxygen here that remains in my alcohol, I'm going to draw this in blue. This is going to come here and bond to this carbon, and it's going to form a bond there. So that means, that the my product here is going to be this 6-membered ring with double bonds. There is an ether group over here that's not participating in my reaction. And then I have this carbon double bonded to an oxygen. And now that carbon is bonded to this oxygen on my alcohol. So now I'm writing this part of the molecule. That's my oxygen there. That belongs to my alcohol, CH, followed by 2 methyl groups. So that is how you can write the product of this type of reaction. Let's do another example. Okay, here are my 2 reactants. I need to predict the product. So the first thing I do is recognize or identify which is the carboxylic acid. I see I have a carboxylic acid on this side. And again, how I know it's a carboxylic acid is because of this group here. Then let's look at the one on the left-hand side. There are a few functional groups here like we saw in the previous problem. I have this hydroxyl group here. So this is going to be an alcohol. But I also have ethers. But again, I know that these ethers are not going to participate in this reaction because I have a carboxylic acid and I have an acid present. So this means that for this reaction, I'm interested in identifying that this is an alcohol. Okay, so I already know that an alcohol and a carboxylic acid will react in the following manner, where the OH group from the carboxylic acid will leave, and it will pair up with this hydrogen from the alcohol to make water. And then this oxygen will go over here and bond to that carbonyl carbon. I'm going to draw that again in blue. So this oxygen here that no longer has a hydrogen is looking for a bond to make, and this carbon here also is deficient of a bond, so it's a perfect match. So they will bond together, and that I'm left with this part of my molecule, so I'm drawing the carboxylic acid part first, and now this carbon here is bonded to the oxygen of this alcohol. So I'm going to draw that first, and now I'm going to draw the rest of this alcohol. Go up, down, I have a 6-membered ring here with double bonds, alternating double bonds, and then my 2 ether groups. And that's it. That's how you can predict the ester product here. So recognize this is an ester and always check that you did make an ester. Right, here's my ester group. Is this carbonyl bonded to an oxygen? I have an ester group up here as well where I have a carbonyl bonded to an oxygen. Okay, and that is what an esterification reaction looks like. Okay, so if we can form it, that means we can break it. If we can go forward, we can go in the reverse. Okay? So the reverse reaction, or the reverse direction, is called a hydrolysis reaction. Again, it's hydro because we're going to be using water to perform the lysis, or the breaking of a bond. What we are lysing here is going to be the ester bond. So the ester bond is going to be this bond here, where it's the carbonyl carbon bonded to the oxygen here. So this is the bond we're interested in breaking. Now, this is also going to happen in the presence of acid. So how water breaks this bond is the OH group is going to replace this OCH2CH3 group. And then this hydrogen that remains will pair up with this group that is going to be replaced to, again, form an alcohol. So this is just the reverse. So now what will happen is this OH group binds to your carbonyl, and then this one here is going to bind to the hydrogen to form the alcohol. So you're going to see that this hydrolysis reaction can happen either under acidic conditions, but it can also happen under basic conditions. When it happens under basic conditions, we have a particular name for this. It's called saponification. The reason we have a specific name for it is because this is a common reaction that we use to make soap. And we will be doing that later in the semester. Okay, so what does a reaction look like under basic conditions? It's going to be the same idea. You are still performing hydrolysis. So you're still going to break this ester bond with water. Okay, so that means this OCH3 group here is still going to be replaced with this OH to make a carboxylic acid. But we're going to have to do an additional consideration here. Remember or recall that when we talked about the acid-base reactions of carboxylic acids, we talked about how when you have a carboxylic acid, so here I'm drawing the product of this OH replacing OCH3 here. So now I have a carboxylic acid. When we talked about the acid-base reactions of carboxylic acids, we talked about how this hydrogen here is what we call an acidic hydrogen, meaning it gets donated as a proton when they're either to water or when there's a base present. And we have a base present here. So what this means is that that hydrogen is going to be removed and or it's going to be removed as a proton. So what is left behind is this negative charge here. So recognize that this product here is really a COOH, where this hydrogen was replaced or was removed, and a negative charge was left behind because it was removed as a proton. It was removed because you have base around. So what this means is that the only difference between the acidic reaction and the basic reaction is that when you form your carboxylic acid, in the acidic reaction you will have this H here present, but in the basic reaction that H gets removed, and so then you have a negative charge left behind. But notice that both reactions are identical. You're still going to make an alcohol in both situations. And then this Na plus is shown here because since we used sodium hydroxide, that metal cation will be floating around. And this is what makes a salt, which we talked about when we talked about the acid-base reactions of carboxylic acids. That is the only difference, but the hydrolysis is going to be the same. Let's go ahead and apply it. So let's predict the hydrolysis product. So hydrolysis, so I know I'm going to be breaking a bond using water of the following reaction under basic conditions. So they don't specify which base, but it doesn't matter. I'm going to know that it's a base. So what this is going to mean is that, first, let's identify our functional groups and our reactants. The first one here, well, I see that I have a carbonyl group, but this carbon is bonded to an oxygen, which in turn is bonded to a bunch of other carbons. This is the definition of an ester. So I have an ester here, and then I have water. I also have a base because I'm under basic conditions. So I know that I can hydrolyze this bond here. I can break this ester bond with the water. So I'm going to rewrite my water molecule like this, where this OH group is going to now replace this here. So this is going to come off. I'm going to go ahead and draw that resulting molecule when I remove that group that I underlined. So this is what I have right now. The OH of my water is going to bind to that carbonyl carbon to make the carboxylic acid. And then the remaining H of H2O here is going to form a bond with this oxygen there to form our alcohol. So the rest of this alcohol is CH2CH3. So this is my alcohol. Now I'm under basic conditions. So what this means is that the H in my carboxylic acid is going to be removed by the base. And what is going to be left behind is just that negative charge. So I have to remove that H there, and it now becomes negative. And that is it. That is how you hydrolyze an ester bond. You replace that OR group with the OH, and then make sure you give your alcohol that H. And that is it. And then if you're under basic conditions, your carboxylic acid needs to have that negative charge. Okay. Aspirin cannot be sold as a liquid for children because it slowly undergoes hydrolysis, meaning that ester bond is going to break in water. What products are formed when aspirin is hydrolyzed under acidic conditions? So the conditions are acidic. So that's just going to inform me on whether I'm going to make a carboxylic acid that has a negative charge or a carboxylic acid that has a hydrogen here. Because it's acidic, that carboxylic acid will have a hydrogen there. So let's go ahead and identify the functional groups in my reactants. Here's my aspirin. I see that I have a carboxylic acid, and then I also see that I have an ester here. So because my conditions are water and acid, that means that these are the perfect conditions for hydrolyzing that ester bond. So even though I have a carboxylic acid here, don't let that throw you off. Recognize that the conditions are for breaking this ester bond here. The ester bond is going to be the bond between the carbonyl carbon and that oxygen. Okay, so that's what we're going to break. So that means that if I break that bond, the OH of water will bond to one thing, and then the H of the other will bond to the other. So I need to decide, where is this OH going to go? Well, that is going to form my carboxylic acid. So that means that that OH has to bond to this carbonyl carbon here. So I'm going to go ahead and draw that on the other side. So that's the carbonyl carbon. So I'm just going to draw that methyl group that's down here and that carbonyl carbon. And now I'm going to add that OH that is coming from water. So that is how I have formed my carboxylic acid. And now I need to add this hydrogen that remains from water to the rest of that molecule that I removed. So here, now this O needs a partner, so I'm going to give it that H. And actually, I'm just going to draw the molecule in the orientation that you see it in. So I'm going to go ahead and draw my 6-membered ring. Then there's a carboxylic acid up here, which did not participate in my reaction. And then I have this oxygen, which was the one that was bonded to this carbonyl group to form that ester. But now, since I removed that carbonyl group, it now needs the hydrogen from water. Okay. And that is how you perform a hydrolysis under acidic conditions. So this means that this hydrogen here that is bonded to my carboxylic acid, that hydrogen stays because there is acid around. Okay. So in the next video, we are going to look at how these very same steps are going to happen, but instead of having an ester, instead of having something like this, an OR group, we are going to have a nitrogen-containing compound.